In this lecture, we shall discuss about goodness of a fit. Till now, in the hypothesis testing, we have seen that we had some sample and we are aware of a population, what kind of distribution it follows, and then we are testing about some parameter of a population. But in this goodness of a fit, we will just have some sample. We will not know anything about the population, what kind of underlying distribution is. We will make some assumption on underlying distribution, like it might be a normal distribution, or it might be a Poisson distribution, or it might be a binomial, or any other well-known distribution. And using this assumption, we go for a testing a hypothesis, and we call that as goodness of fit. And this testing hypothesis on goodness of fit is based on the chi-square distribution. Let us see the steps which involves in the testing hypothesis on goodness of fit. First step is considering a random sample of size n. So we consider random sample of size n, and then we will classify this random n sample into frequency histogram. That is, if some sample has some particular characteristic, we will collect it as a some single class. Having this his frequency histogram, let us say, has k bins or k class intervals. Let us say obtained frequency corresponding to ith class interval is OI. We denote obtained frequency as OI. And as we make an assumption about the underlying distribution, we can use these obtained frequencies to get a expected frequency value. So once we have this obtained and expected frequency value, we will calculate a value. We denote it as chi-square, that is equal to sum of OI minus EI whole square by EI. This is actually, you can observe, the numerator term is difference between the expected value and obtained value. This chi-square value will follow approximately a chi-square distribution with degree of freedom V is equal to k minus 1. And if we observe this value, if we say whatever the distribution we assume that is a good fit for the obtained value, then the difference between obtained value and expected value is expected to be very small. That means this in altogether chi-square value must be small, very small. That means it cannot be very large. So as chi-square is small, we have to go for a testing such a way that we have to reject when we get chi-square is larger than very some particular value. That means we are going to apply here a right-tailed test corresponding to alpha level of significance. We will be applying a right-tailed test. Here the rejection region will be chi naught square, which is greater than or equal to chi square alpha comma k minus 1. This will be the rejection region for alpha level of significance. And we have to take care two important things here. First one is expected value in each of the class interval must be at least 5. So if somewhere if we have expected value is less than 5, then we will add that value to nearby value and make it greater than 5. That means two or more subclasses class intervals we might have to add. And second thing we have to take care is sum of the expected values must be equal to sum of the obtained value. Then only we can go ahead. If they are not equal, there might be some small changes we have to make in the expected value, one or two values, and we have can get the sum of the expected value is equal to sum of the obtained value. Now let us see this with a simple example that is about tossing a coin. Let us say we have tossed a coin for 200 times and 118 times head is obtained and 82 times tail is obtained. We have to test the hypothesis that whether this coin is a biased or unbiased coin with level of significance as 5. That is here given alpha as 0.05. We have to test the hypothesis. Whenever we are testing hypothesis, we have to state null and alternate hypothesis. Let us first state the null hypothesis. We are making a statement about a coin. So coin is unbiased. That is the null hypothesis. And the alternate hypothesis is the negation of this coin is biased. So we have stated the null and alternate hypothesis. Now let us take possible class intervals. So class interval, if we observe, either head is one class interval and tail is another class interval. We have two possible class interval, head and tail. If we go for obtained values, head is obtained 118 times and tail is obtained 82 times, and corresponding expected value, if I want to list, if we have a fair coin, if I toss it two times, one time I have to get head and the other time I have to get a tail. That's what we expect in a unbiased fair coin. But as we have tossed here 200 times, we expect that 100 times we are going to get head and remaining 100 times it will be tail. Now if I go for calculation of the required test statistic chi-square, this chi-square value will be obtained sum of obtained value minus expected value whole square by expected value, that is 18 square by 100 plus 18 square by 100. This will get it as 6.48. Now we have a chi-square value calculated. We have to go for observing the acceptance region or rejection region. So here acceptance region will be chi naught square less than or equal to chi square alpha comma k minus 1. Here chi square alpha is 0.05 and k minus 1 is 1, and we will get this value as, we can get it from the table, this value is 3.841. This value is 3.841. 3.841 is the acceptance region. Any value less than 3.841 will be acceptance acceptance region. But we observe here we got 6.48 is the observed test statistic value, but this is not less than 3.841. That it means it is not in the acceptance region, it is in the rejection region. Therefore, we have to make a decision here. Decision is the given coin is not a, or we have to reject the null hypothesis. That means we have to reject the hypothesis that the coin is unbiased. That is, the coin is the coin is an bi is a bi biased coin. So this is the conclusion we can make from this testing. Let us see one more problem. Here I have considered a data which is assumed to follow Poisson distribution. Let us see whether the assumption of that data follows Poisson distribution is correct or not. Here a table is given. in which the number of defects observed in printed circuit board is listed out. 0 defects were observed in 32 boards and 1 in 15, 2 in 9 and 3 in 4 boards. Now according to this, let us make a hypothesis. First one is null hypothesis, that is number of defects in printed board follows Poisson distribution. Second one is alternate hypothesis, that is it does not follow Poisson distribution. Now we know that Poisson distribution, where probability mass function is given by lambda power x e power minus lambda by x factorial. Here in a Poisson distribution, lambda is the parameter. Lambda is nothing but the mean of the Poisson random variable. Here if I consider mean of this Poisson random variable, we get it as 0.75. So for this lambda will be 0.75. Using this lambda value, let us determine the expected value. That is, first let us determine probability of x is equal to 0. Here by substituting x is equal to 0 in the probability mass function, we will get probability of x is equal to 0 as 0.4724, and this value is corresponding to one board. As we have 60 board, if I multiply this probability by 60, we will get expected number of boards having zero defect, that is given by 28.342. There will be 28.342 boards with zero defect. Now similarly we can calculate the number of boards with one defect, two defect. As we know that in Poisson random variable can take any infinite number of values. So as we cannot go on calculating each and every value, we'll simplify our work, that is probability of x greater than or equal to 3 will determine, that is equal to 0.046, and the corresponding expected value will get it as 2.4303. Now again I have written a table in which the number of defects, observed frequency and expected frequencies are listed. We can observe here sum of the observed frequency is 60 and sum of the expected frequency is also 60. Actually the second condition is fine, but if I observe the first condition, that is each of the expected value must be at least 5, but here the last value, expected value for number of defects 3 is less than 5. That means I cannot go directly with these values. So this is number of defects greater than or equal to 3. Now as we discussed earlier, we have to add this to nearby value, that is number of defects 2. So we have an updated table, that is number of defects 0, 1, 2 or more defect. So now we can observe each of the expected value is greater than 5, and let us calculate the test statistic, that is chi-naught square. We get that chi-naught square as 2.9628. Once we have this chi-naught square value, we need to determine the acceptance region. Acceptance region acceptance region will be chi-naught square less than or equal to chi square alpha comma k minus 1. Here k is, because we have 3 class interval, k will be 3, k minus 1 is 2, and given that we have to use 0.05 level of significance. Now if I go back to the table for degree of freedom 2 and alpha 0.05, chi-square value is 5.991. If I this value is 5.991. We can observe here the test statistic we calculated, that is 2.9628, is less than 5.991. 5.991. Therefore, this test statistic is in the acceptance region. So we have to make a decision, that is the given data follows the normal distribution. That is the null hypothesis we have to accept. Sorry, null hypothesis we have to accept. That is the given distribution follow given data follows the Poisson distribution. Let us see quickly one more example. We'll fit a binomial distribution for the given data, and then we will go for testing how good that fit is. So here we are given the binomial data for 0 success, 1 success, 2 success, 3, 4 and 5 success. Now if I want to fit a binomial data for a binomial distribution, we know that there are two parameters, the total number of trials we are taking n and the probability of success. Here we can observe there are maximum of 5 success. That means that number of trials we have taken is 5. Let us not get confused with the sample size. Sample size is different. Here the number of trials in a binomial distribution is different, but notations are small and always for both. So n is 5, no doubt, but I need to determine p. We have a formula for mean in terms of n and p in binomial distribution, that is mu is equal to n into p. Now using this formula, if I determine mu, we can calculate the p value, probability of success. So I have determined the mu value using this frequency distribution. We got it as 2.84, and using mu is equal to np, we have obtained the value of probability of success, that is 0.568, and corresponding to x is equal to 0 to 5, I have determined the probability of success and the corresponding expected value. Just I have listed it out here, obtained values and expected value. You can observe here sum of the obtained value is 100, but sum of the expected value is 99.99. So as I have to make a rearrangement, I have to add 0.01 somewhere. I'll add it to the first one because that is a small value we have. I am adding it to first one, 1.51. And also we can observe here this first expected value is less than 5. We cannot proceed as it is. We have to add this value to the nearby value. So if I make a rearrangement, the first data will be corresponding to 0 or 1. Second one will be for 2, 3, 4 and 5. Correspondingly we have obtained and expected value. From these obtained and expected value, I have calculated the required test statistic. I got it as 3.9954. Now we have to go observe the acceptance region. Acceptance region will be chi naught square less than or equal to chi square 0.05 comma k minus 1. Here we have k is 5, so k minus 1 will be 4, and chi square 0.05 corresponding to 4 will be 9.488. This value is 9.488, and we can observe that the test statistic we calculated is less than the critical value. That means we have to accept the null hypothesis, that is the given data follows a binomial distribution. Thank you.